And our last example, I think it's the last example of programming style that can be supported by monadic operations is a non-determinism. And this one is quite nice in some sense because, I mean, so far we've had this box and we've put some things in the box, and there would be at most one instance of the thing in the box. So for option, it would be 0 or 1. For state, it would be 1. With non-determinism, you can have a whole bunch of different values, right? So non-determinism is very nicely modeled just by sets, right? So a program that can either return 1 or 2 is a program that can return the set 1, 2. So you can think of non-determinism as determinism, but with sets. And this is what we're going to do essentially. So pure just and okay. Well, first, what is a set? Right. Well, a set in Lean is defined quite easily as a synonym for the predicates over alpha, right? So, if you have a predicate over a type, then it's going to say, oh, for this element is true, for this element is false, for this element is true. And sets are the same, right? So you can say, well, being true is the same as being in the set, right? So sets and predicates are isomorphic, and in Lean they're definitionally equal. So that was for set. And there are some operations on set. I mean, they're documented to some extent in the guide. And the first thing we do is pure. Well, pure is going to be easy. If we want no effect, we just want the pure value, then we do a set with, we create a set with only that value, it's a singleton set. Bind is a bit trickier. I mean, conceptually, it's very easy. So it's just the writing that looks confusing, right? So we start with, I mean, bind starts with a set, and then which we call big A. Then we have a function f, and we have to create another set. So we're going to create the set of all b's such that there exists an A where the A is in big A and the B is in f of A, right? So we start from big A, we take any element, right? And then that element we pass to F, and then F returns a whole bunch of elements again, and we take any element B, and then that's what we put in the element, in the set. Indeed, this is how non-deterministic programming works when you do combinations. So suppose your first step returns either 1 or 2, and your second step either multiplies the result by 2 or by 7, right? Well, then you end up with 4 combinations, 2 times 2, right? Because you could say, well, non-deterministically, you take the left possibility, the first possibility in the first case, in the first statement, and then the first in the second statement, or the first and second, and so on. And this is exactly what we're doing here with this set comprehension. Now, right, we need to prove things. Associativity is a bit problematic because we have this big, horrible formula here. But again, a good intuition is that when you compare two sets, it's a bit like you're comparing two functions. So you want to apply functional extensionality. But there's even in Lean something called set extensionality, which works even with set syntax. And it works, you see, it says if X is in the set such that blah, and here you can simplify all of this, right? So if X is in the set, containing all Y such that certain condition, you can simply apply the condition directly to X and get rid of, both the elements operator and the braces, right? So that's what we do with simp. And then we get pure logic. But the pure logic is a bit cumbersome. So here I didn't want to write a 20-line proof, just tearing things apart and so on. So I use a tactic that can do this for me, and it's called tautology. And it just finishes the job here. Right. It's not a very important tactic in this course. It might be that you never need it for anything, but here I needed it, so and I've introduced it. And as the course progresses, I want to show you that Lean has more powerful automation than just intro, apply, CC, and rewrite in Sim. So it's good that we still progressively learn new tactics all through the course, and there are many, many more. I mean, we're just scratching the surface in the course. Okay.